For our fourth lab, we examined the motion of a spring mass system in which the mass swung in an arc while oscillating on the spring. So some basic concepts that are behind this lab and some little history here. Galileo is basically said to have been sitting in a church watching a large chandelier swinging back and forth when he decided that the period of that pendulum, so the swing, was constant and was independent of the amplitude of the oscillation. A periodic motion is one that represents itself in a fairly regular way. The time it takes for one full motion is known as a period. Period is represented by t, and a quantity related to the period is the frequency. Frequency is the number of oscillations per second. The frequency and period are related by f equals 1 over t. Another quantity which describes the periodic motion is the amplitude. The amplitude is the maximum displacement from the equilibrium position of the motion. A particular type of periodic motion, where the motion repeats in a sinusoidal way, is called simple harmonic motion, which is basically what we're going to examine today. So the example that we're examining is the oscillations of a pendulum when the displacement is small, and the oscillation of a mass on a spring. When a spring is stretched or compressed, the force required to stretch the spring is given by Hooke's law, F equals minus kx. The normal method of analyzing the motion of a mass on a spring using Newton's second law leads to a differential equation, which is kind of beyond the scope of this course, but we can state the result for the period of a mass on a spring as shown on the right. So, on to conducting our visualization. So, for Tracker, I placed all the videos into Tracker, and I put a point mass, and I basically analyzed the position with the x and y of the mass on a pendulum. Important information that was extracted from the video previously shown was the time, x position, y position, initial velocity, which was 0, the mass, gravitational acceleration, which we already knew, period, spring constant, and L0 length of the spring for the coding section. So for initialization, we didn't pretty much have to change anything because the delta t was the same. All I did was add the ball's mass, the ball's position, and the ball's velocity, which was already 0. So for interaction constant, springs, and energies, I added g, spring constant, relaxed length of spring, and I edited the next 3 lines to specify the vector L, which described both the length and orientation of the spring, as well as computing the system energies through given code. Here, for the calculation loop, the initial energies were defined. The gravitational force was calculated by minus ball mass times gravity. The spring force was calculated, and the net force was calculated, which is F spring minus F gravity, plus F gravity, but F gravity is negative, which makes it minus F gravity. Then the object's velocity was updated, and the object's position was updated. So then the spring was also updated using the same lines of code written to calculate the vector L, which describes both the length and orientation of the spring, and the trail was basically graphed. Then the energy changes were calculated as shown here on the left. Our results. So the blue represented the predicted motion, while red represented the observed motion. As you can see, these are pretty close. Blue is just a translation to the left of the predicted motion that is represented in here. So for the change in energy versus time, the blue here represents kinetic energy, while red represented the gravitational potential energy, and green represented the spring potential energy. Finally, yellow represented the total energy. Since we had our system with all of the components inside, there was no change from the inside to the outside of the system, which means that the yellow was 0. Therefore, as you can see, all of these energies added up to 0 as they were oscillating. Is the energy principle satisfied? As I explained briefly a while ago, the energy principle states that the change in energy is equal to the energy input from surroundings. The change in energy is the total energy of the system, and as I said, it stays constant. So the energy principle is satisfied. It is 0 because there is no energy transfer with the surroundings. The change in the total energy of the system stays constant throughout the oscillations, as one potential or kinetic increases, the other one potential or kinetic decreases. So there are opposite phases shown on the graph. If we're to make 2 separate estimations of oscillation periods, as you can see on the left, the period is given by 2 pi square root m over k. Therefore, the equation for both periods is the same, and it is path independent for the path that the spring is taking. Therefore, since the properties of the spring will be the same, we know that the periods for both oscillations will be most likely identical because the mass and the spring constant is the same for both oscillations.